All right. Let me stop transcription. Good. Welcome, everybody. This is Hardware Systems lecture on cache memory hierarchy. All right, so hopefully you had a good Thanksgiving break. Today we will have Cache Lab. So for Cache Lab, there would be two problems. So I would go over problem one first, and then I'll make another recording for Cache Lab problem two. So there are two problems, right? So two videos. Yeah, the reason I'm recording is I may not be able to come to the class, so it's better to record a video so that the teaching assistants can show the video, and then you can carry on with a lab on memory hierarchy and in particular cache memory. All right, so let's get started. In the last few lectures, we have been looking at introduction to memory hierarchy. So in that lecture, we looked at memory mountain, which basically talks about uh, what is the impact of strides, like the step size that you take while going over the array versus what's the impact um, um, with respect to the size of the data. So we were looking at spatial and temporal locality. Spatial locality depends on the strides, and stride size could be 1, 2, 3, 4, and so on. We looked at that in the memory mountain. And the data size is for temporal locality. How big is the data? Does it fit in the cache? If it does not fit in the cache, then least recently used strategy would be used to evict uh, the member from the existing cache, right? So the idea is least recently used item gets removed to make room for a new item to be inserted to the cache. So that was what we looked at. The final thing was memory mountain. And after that, we went to the next topic, which is how do you implement hardware cache? So hardware cache are already implemented, right? We have phone, we have computers, laptop, and all of these, they come with cache implementation. So there is SRAM. How is it designed? So there we looked at direct mapped cache. We have not looked at fully associative or set associative cache yet. We have looked at direct mapped cache, and there the basic idea is that um, when item goes from large memory to the small, then you can either do modulo operation on the size of the cache, as memory address modulo size of the cache, that will give you where D would be located, or the next method was basically pick the least significant bits, like three leftmost three significant bits you take, and that will tell you where does the address would be stored, right? So that's what we looked when we were covering direct mapped cache, right? We talked about cache tags. Like, remember when you check in your bags in a hotel, they give you tags. So tags are important so that whether it's a hit or a miss, the item is it already there in the cache or not, because different addresses can go to the same memory location. So that's why you need tags. And then we also talked about valid bits. We did some demo on direct mapped cache. Basically, as addresses are coming, where would you put them? And you see there are some hits, there are some misses, and that's what we captured. The last slide was direct mapped cache, the hardware to implement that, which basically uh, is made up of logical elements like and, comparator, and the tags are used to basically check whether the tag of the address is equal to the tag in the cache itself, right? So this is all something that we have already covered. And this was the last quiz that we did. Now, going forward, I do have to cover set associative cache, but I will not do that today because we have a lab. We have a lab today, so I better be covering materials that are uh, going to be used in the lab, and we will carry on with set associative cache in the next class. So today, my lecture will focus on lab material, which is basically if we have some program, how do we make sure that the program is uh, performant, meaning you are getting performance from your program, and it does have to do with how do you access main memory, in what order do you access main memory. So the main memory does need to have some data. So let's say the data is a matrix, so matrix like two-dimensional matrix, and we will see some programs and look at the access pattern, memory access pattern, like how is it being accessed and what is its impact on performance. So to relate it with the older slide, this is related to stride. Okay, so just remember stride would be useful here. All right, and this some of the material is from a different book, so this is not the main course book. uh, this has some material from Computer Systems, a Programmer's Perspective. All right, so yeah, let's get started. So problem one has to do with a matrix. So let's look at matrix. So here, what I'm showing you is a two-dimensional matrix. So it's possible that you might have already seen a two-dimensional matrix. If you have not, then this is how it works. So this matrix is 4 by 4. So 4 rows, 1, 2, 3, 4, and 4 columns, 1, 2, 3, 4, right? And the way we name them is we first give them the row number and then the column numbers, right? M00, that means 0 is the row number, 0 is the column number. Let's look at this one, M03. So 0 is the row number, that means it's the first row, starting from 0, that's why first. And the column is 3, so first column, second column, third column, fourth column, right? That's how we index our matrices. Now, a programming language like C would first store the first row. So you see the yellow part, which is the first row. And then the second row is stored in main memory, because main memory is not two-dimensional. Our view of main memory is that it's a linear storage, right? It's one-dimensional linear. So two-dimensional thing behind the scene is stored as one-dimensional. So you have the second row, then you have the third row, then you have the fourth row. Now this has implication on performance. Okay, so if you traverse the matrix in row by row, it would be faster because row by row is laid out linearly in the one-dimensional view of the matrix elements being stored in memory, right? But if you go column order, then that's going to be a little bit uh, you know not ideal traversal with respect to performance. Okay, so let me talk about the column order traversal. So if you go vertically, then it's called column order. For example, M00, then you access M10, then you access M20, and finally you access M30. That's called accessing a column, or this is a column major order. Okay, all right, now let me highlight another fact. So M00, right? It's over here. And now let me go to M10. M10 is here. So if it's here, right? And M20, it's over here. So if I'm accessing elements M00 and then M10 and then M20 and then M30, you see that I'm jumping, right? So it is a stride of 4 elements. So 1, 2, 3, 4, and then the next. 1, 2, 3, 4, and then the next, right? So if you access the elements of a matrix in a column major order, then you are jumping, or you are having a stride of size 4. And stride of size 4 while accessing the matrix is not good because uh, you know, the way the main memory and caches interact is uh, block by block. Things are copied. So let's say this is main memory mm, and this is cache. Okay. And so what happens is you basically pick a block. You don't pick one element, but generally it's a block, meaning multiple elements. Let's say 4 elements. So 4 elements are copied and placed in the cache. So let's say those 4 elements were stored here. So because accessing one element makes the hardware to bring a block of elements to the cache. That's why if you are accessing M00, then you get M01, M02, M03 for free, right? So this example is like if there are a bunch of books on a table and I have to carry books from one table to another, then instead of picking book one by one, I would basically grab 4 books at a time and then uh, transfer it from one table to another. So that's a way more efficient than doing one by one. So that's the way caches also work. Now, what is the block size? It may vary from machine to machine, right? So generally, it's a fixed parameter. It may vary, but the idea is that whenever one element is accessed, the computer will basically bring that block to the cache. Uh, and so that's the basic concept. And because of that, if you are doing, M00, M01, which is a row major order, then, the first element M00 will not be in the cache. But the moment you fetch M00, then these 3 will come and will be available in the cache. So we say that for the first item, there is a cache miss. So let's say miss, but for the next 3 items, there is a cache hit. Okay. And this happened because the block size was 4 and 4 elements were copied at one time from main memory to the cache. All right, so that makes sense. So now you have to be now you should be able to see the difference between uh, going through the matrix in a row-wise fashion versus column-wise fashion, because that will make a difference. Okay. So in the first exercise in the lab, you would be practicing this concept. Okay. All right, let's carry on. Good. Now I'm showing you, 2 ways of traversing, right? So just continuing with that previous point. So let's have the laser pointer. Yep. So a row measure, right? So here the indices are starting from 1, but the idea is same, right? Row by row you're going. So this program over here is row measure traversal. So let's look at that. So you have how many elements you have in the matrix. So 3 times 3 is 9. So that's why it has to run 9 times. So n is 3. So for each value of I, this inner loop will run 3 times, n times, right? And I is equal to 2, again this runs 3 times. I is equal to 3, again it runs 3 times, right? So it's n square times this program will run. And the way the elements are accessed is A11, then A12, then A13, then I would become 2, so A21, A22, A23, and so on. So you see that this is row major order. All right, now let's go here and see that this one is different. Aij, this one is Aji, right? So this one is doing something else. So this one is column major traversal. So column by column, it is traversing. And in programming languages like C, this is not good. But for other programming languages like Fortran, column major order is better. Okay, so it is dependent on programming language as well. So in C, C++, Java, traversing in a 2D matrix is a stride 1 axis in row major. So that's efficient. Okay. So here we see you have I, you have J, and Ji, right? So J is the inner loop. So this number would keep changing, j would keep changing. So 1 1 2 1 3 1, right? So that's what is the column order. 1 1, then j becomes 2 2 1, then 3 1. You see? Yeah, that's the column. Then I becomes a 2, so 1 2 2 2 3 2, right? 1 2 2 2 3 2. Then I becomes a 3, so you fix this as 3. You fix this as 3 because I is now 3. Then j would become 1 3, then 2 3, then 3 3. So you see that this went over this column. All right, so this is the column major order, and this one is a stride 3 axis. Okay, it is not continuous axis in column major because the 2D matrix is stored in a 1D manner, but in a row major order. All right, so this is very important to understand for your lab problem number 1. All right, good. Yeah, if you have any question, you can email me. If I'm in class, then you can definitely ask in the class. Uh, so let's practice some whether we understood this problem or not. Row versus column. So there are 4 rows in this matrix. You can see 4 rows, and then you have 5 columns in this matrix, right? So to repeat, A21 means is the second row starting from 0, 0th row, first row, second row, and the next index is for column. So it's the first column. So 0th column, first column, second column, third column, and so on, right? So first we write row number, like 2 is the row number, 0 is the column. All right. So this is a, I mean, this one is a 4 by 5 uh, matrix. So there is a typo here. There are 5 columns. Okay. All right. So if you do this piece of code, is the following statement true or false? All right. So you want to add a bunch of elements from the matrix. So a 0 0 0 1 0 2 0 3 0 4 0 0 0 1 0 2 0 3. So is this row major order? Yeah. Think about it. Right. It is, right? Yeah, so this is row major order. Let's go to the second one. Second one is also adding a bunch of numbers, and the question is this order column major? So let's see. 0 0 1 0 2 0 3 0. So this is column major order, right? So I picked the first column, but it can be any column, and that would be a column major order. So this is also true. Both are in fact true. All right, and now let's look at next pop quiz. So A30 here, A31, A32, A33, A34, right? So this is again a row major order. Okay, true. Now let's go to the second problem, B. Is this column major? So let's see, 0 4 1 4 2 4 3 4. So this is column major, right? It is a, or the axis pattern is column wise axis. Okay, so both are true. All right, now let's look at the next one. A00, A11, A22, A33. So is the sum being calculated in a row major order, row wise, column wise, or neither A or B, or depends on whether it's a C++ code or Fortran code. So Fortran is a programming language. You might not have used it, but many people use it for scientific computing, in mathematics also. Formula translation. Yeah, it's older programming language. All right. So what do you think? 0 0 1 1 2 2 3 3. So this is neither row major nor column major. Okay, and you can see, right, it is actually a diagonal order. So diagonal order is neither row major nor column major. All right, so answer would be C. All right, now let's look at um, this slide. So sum is being calculated by adding 4 things. How many cache misses will happen if block transfer size for caching is 4 integers. So this says that the block transfer size for the elements of matrix, 4 things are getting copied at a time, right? So 4 items from the main memory are getting copied to the cache. So block size is 4. So how many cache misses will happen if you do A00, then A11, A22, A23, right? So we were doing this kind of analysis for in our first lecture on memory hierarchy, but it did not have a cache. I mean, it did not have a matrix, right? It only had some elements in a one-dimensional array, but this is two-dimensional array. All right, so let's practice this one. How many cache hits will happen? So A00 and A10 are, oh, this I'm showing you. Yeah, this is showing something different. It's not, does not correspond to this one. Here I'm showing that if you go from A00 to A10, it's so far away. So even if you had a block size of 4, accessing A00 might bring you 4 items, like these 4. I mean, these 4 A00 to A03s are still A10, will not be there in the cache by virtue of block transfer. So you need to access A10 again. So there would be a cache miss for A00, A10, A20, A30. There would be cache misses for all of them because a block size is only 4. All right, so whenever you access A00, then you'll get 4 items. And then when you access A10, there would be a cache miss, and you would get the next 4 items. So when you access A20, then again you have cache miss for A20. It's not there in the blocks. And LRU scheme would take evict the older items, and only least recently used items would be evicted. A30 again will create a cache miss. So the purpose of this is to show that if you were doing A00 plus A10 plus A20, then how many cache miss will happen if you're just selectively adding a subset of the elements but not all of the elements, right? You're just interested in adding few elements. So you can also see that this is a stride size 5. A00 to A10 is a stride size of 5 because you're jumping over many elements. So if you have to calculate sum by adding a bunch of elements, there would be 1 cache miss, 2, 3, 4. So there would be 4 cache misses in this program which accesses these 4 items from the matrix. So then the question is how many cache misses we'll have for this one, right? So A00, initially the cache is empty, so A00 would not be available in the cache. So you have a cache miss for A00. Then because the block size is 4, so these 4 items will be loaded in the cache. So A04, A10 is not in the cache. So when you access A11, there would be a cache miss. So 2 cache miss, right? 1 cache miss for A00, another for A11, and then you access A22. So there again, the block size can have like 4 items. So again, you're not able to get. But when you get A22, then A23 would be in the cache because A22 and A23, will be copied in the cache because they are like spatial locality will happen. This is stride 1 access, right? So there would be no cache miss. A23 would be a cache hit. All right, so there would be only 3 cache misses for these items being added to produce a sum. Okay. All right, so this is just a way to think about cache hits and cache misses based on spatial locality. All right. So what is the lab problem? Lab problem is you would be given a row major program. So you need to basically add all the elements in this matrix. So that's what this program does. It uses 1D access to basically go over all the elements. So you have to assume that SRC is the matrix in a one-dimensional way. So it is 3 by 3. Visually it looks like 3 by 3, but it's a linear order 9 elements, right? So it's a one-dimensional SRC array with 9 elements, and this is accessing all the elements in a row major order, and you are printing the sum. So I is 0 in the beginning, so it is j would keep changing. Then I would become 1. Then it is this is a n by n matrix. So then you go to A21, A22, A23, then A31, A32, A33. So it goes over. Now you have to write a program that adds in a different order, right? So that's what the homework problem is, and um, you're given some source code to get started. All right. So matrix addition.c, the program would be provided to you with this part blank. Matrix is being created using dynamic memory allocation. How many elements are there? The number of rows is equal to number of columns. So 3000 times 3000 is a big matrix. You initialize the elements, and then you note down the time. How much time does it take using get time of day, and then you call your column major and then see how much time it took, right? Yep, so this is what you will implement. All right, so that's the problem number 1. Now I do have to the problem statement looks like this. So let me see if I have. So this is a problem very similar to the previous problem. Yeah, so the next thing that I want to highlight is about a tool that you have to use. So perf is the tool that you have to use. So remember, in your, I believe it was the first or second lab, you used perf tool, and this is a performance tool, right? A perf stat will show you the statistics. And the reason you used this tool earlier was to find out the clock cycles per instruction, how many instructions are there in your program. So all the CPU related statistics you were able to uh, print by running a program, right? So you have already used perf, so you can look at your previous lab to see how you used perf. But in this lab, we would use something different. So perf does let you work with CPU statistics, clock cycles, and instructions, but it also uh, lets you display or print how many cache loads happen when your program is running, how many misses happens, right? So the cache, this miss is the cache hit, cache miss, right? So load meaning how many loads happen from main memory to the cache, and misses means the item was CPU looked at an item in the cache, but it did not find. So that's the miss. So load got missed. So you want to know, out of your L1, L2, L3 cache, this is only for L1 cache. So L1 cache is the level 1 cache. This is the first cache closest to the CPU, or let's say arithmetic and logic unit, ALU. So your matrix multiplication program, you can run your a.out or whatever name you provide here for your matrix multiplication. It's the name of the executable, and then it will show you. So I did this experiment. So I did this row major matrix addition, and I found that there were about 144 million cache loads, and this is something that the hardware is telling us. And then it also displayed me the number of misses. So a million misses happened. So this is like 0.76% of all the loads. So you see that there were very few misses, right? So this is 0.76% out of all the loads. Now on the column major, there would be runtime difference as well, which you should check. But you will see that there are more misses, right? So 1 million versus 9 million. So there would be lots of misses. So we see that the column order traversal while doing matrix addition, which you'll develop and then run and use the perf command, uh, you know, will show you more misses. So the idea is, first you do this timing, this statistics only using the row major, and then disable row major and enable column major, and then do, cache miss for this. So it's hard to distinguish between two functions. So do one by one. So first measure how many cache misses happen for row major, then comment it, right? And then only do for column major, right? The code that you see, that you wrote. All right, good. Now, in the materials for the lab, I have some explanation for matrices and traversal, so you should read them. It's quite good. And what I'm showing here is another way of saying that the two-dimensional way and one-dimensional way is actually equivalent. Okay, that's what this table shows, that they are equivalent. So yeah, let me highlight that point. So a matrix like Aij can be accessed using row number, column number, and that's why you have two numbers for each access, A00, A01. But equivalent way of accessing is A0. I should have written A0, A1, A2, and so on, right? You can access the elements of the matrix as if they are one-dimensional. Oh, looks bad. Okay, but you get the idea. These are array accesses, 1D access, right? So 2D access and 1D access are equivalent because you can go through the array pretty much in the same way, right? You can do a row major traversal in 2D, and you can also do the same thing in 1D, right? The same vice versa for a column order traversal as well. So this is showing you that A00 is in fact the first element. A10 is the fifth element in that order, linear order. A20 is the 10th element in the linear order. A30 is the 15th element in the linear order, right? A30, this one is the 15th. So you can start counting 5, 5, 5, 10, 5, 3, 15. So you see, starting from A0, so A15. All right, so this point is very important to understand. So ask your teaching assistant if you are not able to see that both of them could be used to access a 2D array. So you could represent arrays in two different forms, 2D or 1D. But once you have represented them, then you can access them. If you have 2D, then you use row number, column number. If it's 1D, then you just need which index. All right. So I provide you some guidance on what is the command. Now be careful on, I mean, copy paste may work, but if copy paste for this command does not work, then type them up. You have to be careful while typing them up. I think copy paste should work. All right. Yeah, the next part also has LLC misses. So as I said, you said that L1 is not the only cache. So this perf command also lets you do last level cache. So LLC is last level cache. So you can also get LLC load misses, right? So this is like cache misses, but for not for L1 cache, but for LLC, that's the L3 cache, last level cache. And you can fill your table, like how much you collect the statistics like misses and how much execution time and load, and you can see you can see what the numbers look like. Okay, now all of you are accessing the computer at the same time, so you may get numbers that are kind of, how to say that, noisy, because if you do access a computer one by one, then you'll get I mean, your program can interact with somebody else's program because many people are using Pascal at the same time, so that may give you some uh, noise in the data. But it's a good exercise to just see what's the experiment that we're trying to do, so that whenever, I mean, this is a toy program, but in your real life, if you see a program and you want to see, I change the order and what's the impact. So you could do this experiment. Now this is a toy problem, but the next lab assignment, I mean the next lab problem is not so easy. I mean that's a matrix, but it's tricky. Okay, but this one is an easier example to get your hands dirty and understand the concept. So in problem 2, we'll see matrix multiplication, and this is a little bit tricky to understand because there are lots of computations in matrix multiplication. Matrix addition was easy problem, and there also you have to do the same experiment, like measuring loads and misses and what's the time. My sample program also calculates how many gigaflops happened. That means how many floating point operations happened. It's a rate per second, and giga is like 10 to the power 9. All right, so we'll talk about lab number 2, the second problem later, but this is the first problem. All right, so now the first problem is over. Now I'm talking about simpler thing. So my analysis before was using a model to calculate cache hits and cache misses. Okay, it's a model because you really have to make a model to do some analysis, because different vendors like Intel, AMD, ARM, they'll make their caches in a different way. The processors, the implementation may be different. The hardware is different. So we only use a model that helps us and analyze the performance. But in in generality, in actual scenario, it is complicated. So there are lots of things that happen. For example, hardware prefetch. So what is hardware prefetch? So prefetch means accessing something before it is being needed. So let's say your program is running and you have to access a lot of data items. So as you're accessing an item, the CPU is trying to figure it out, like which is the next item that I should bring to the cache from main memory, right? Which is the item that I should bring from main memory to the cache before it is being used. So that is called prefetching. So the hardware tries to learn the data access patterns in a running program. So as your program is running, it can figure out that, looks like this is the access pattern, so I should bring the data before it is being used. Okay, so this has to do with prediction, machine learning that the hardware does, and those are basically guided by spatial and temporal locality. So hardware prefetch is an optimization to improve the runtime, right? It's an optimization to make our programs run faster. Because memory access is very slow. So as I already told you, that it takes 100 nanosecond to bring something from the main memory to the cache. So it is actually very long time. Now in a CPU, if the data item is available, then you can work with the registers very fast, in like less than nanosecond, right? You do many arithmetic and logical operations in the CPU. So this is the cache and this is the CPU. And even you can access your L1 cache in like 0.5 nanosecond, 1 nanosecond, varies, but it's very fast to access a cache memory from the CPU. So because accessing main memory is so slow, that's why prefetching is a good idea, because it brings something that you already need. Okay, and the computer does its best to do prefetching. All right, so the next video would be on matrix multiplication. So I stop here. It got hanged, but you can stop here. I'll make another video for matrix multiplication.